Hello everyone, and welcome to another member sponsor video hosted by Mr. Logan Frank. Logan, this here is part 3 of our little mini series covering how to create Pong with Python. Tell us a little bit about what we're going to be doing in this video.
Well, in this video we're going to create the ball class.
Okay.
That means we're actually going to subclass the actor, and we're going to give it some ball-specific functionality. We're going to modify the way that movement works so that the screen bounds are checked, because that way the Pong ball can bounce off of the top and bottom of the screen. And if it goes off the left or right-hand side of the screen, that counts as out of bounds, and the ball will reset itself and relaunch itself from the center of the screen.
Okay.
We're also going to address a method called launch, and that method's job will be to send the ball off in a random direction at a given speed. So we're going to run some calculations though, so we can get an expected speed and simply point that in any desired direction we wish.
All right, sounds good.
Once we've got that in place, we'll make we'll switch our ball test object over to be an actual type of ball, and then we'll use that to just make sure that we have our bouncing code and our out of bounds code working.
Okay.
So to begin, we're going to create the ball class. To do that, I'm going to jump in right after the definition for the actor class, and we will make the ball class. Class ball. Now, of course, ball is going to inherit from actor. And now we're going to make sure we add on to the move method. So I'm going to define a move method for the not underscore, just our own custom move method. Just like in the actor itself, we're going to be taking in a self for the current instance, and we're going to give an amount. And let's see, one other thing for the ball itself, looking at this, I think I'm just going to go with move and amount.
Okay.
There is a case later we're going to modify launch a little bit differently, where instead of taking in an amount, we give a speed, and we allow the velocity to auto-set itself.
I see.
Now, as far as move, the first thing that we want to do in the ball's move is make sure that the actor, the parent's version of the move function gets called, because move does some required things back up in actor. If we look here, it increments the position, and we want to have the same thing happen for the ball itself. So we make sure we call actor.move and feed in self as the instance and amount as the amount to move.
Okay.
So, after that, the next thing we're going to do is we're going to do some additional checks. The reason that we're modifying the behavior of the move function here is we want the ball to not only lock itself to the screen, but we want to check for bounces. Mm-hmm. So basically, every time a move occurs, we're now in a new location. So we need to check where we are in relation to the top, bottom, left, and right of the screen, and use that to determine if we should actually bounce or not.
Okay.
And so to do that, we're going to move into some if statement checks. I'm first going to check the top and bottom of the screen. So we can begin an if statement. Inside of that if statement, we'll check self.position.y, and we'll see if that value has gone less than 0. If it has indeed gone less than 0, then we know we've hit the top of the screen. So we're going to bounce into the down direction. So we're going to say self.velocity. If a little bit of spelling, self.velocity.y. Now I'm going to make the velocity reversal here a little bit more advanced than we did in the test program. In the test program, I simply reversed it. And the moment we saw we were less than 0, we reversed it. There is a danger in the way that works, and that is if for some reason the reversing that velocity does not completely eject us from the wall, meaning it does not get y greater than 0, then we run into a scenario where the ball will simply stick to the wall and vibrate back and forth, because on the next update we're still on the wall, so we move forward towards the wall again. Now we're further in the wall, so we move a little bit out, but that doesn't get us out of the wall, so we get stuck in that scenario. What I'm going to do here is I'm going to look at the velocity y and get the absolute of its value, because we know by this check we have hit the top and only the top of the screen, and that means we need the ball to be moving in a downwards direction. Down, in this case, the way the screen coordinates are set up, is a positive y. So that means take whatever value is in y, preserve that value, but make sure that it is positive, and that is the function of absolute. So make sure that our value in y is set to math.fabs, so we get a floating absolute value of self.velocity. And if I can spell velocity, we'll continue. Self.velocity.y. There we go.
Okay.
and then of course we'll return positive velocity. Now I'm going to do an else, or an else if, so elif the position has gone past the bottom of the screen. So if self dot position dot y is greater than the screen height minus the overall width, because again, we don't want the top of the ball to collide with the bottom of the screen. We want the bottom of the ball to collide with the bottom of the screen. So we need to make sure we offset by however tall the ball actor itself is. And we'll do that by looking at the getBounds method, because of course that gets our current screen rectangle. And spelling has just left me at the moment. There we go. I guess I'm trying to plan out how much is working a little bit too much and forgetting about spelling. But we are looking for bounds.height, and that makes our offset. So again, just a quick recap on this, since it's somewhat of a long line. Making sure that we check our position Y to see if it is greater than the screen height minus the actor height.
If we have to take into account the actor height, because otherwise it'll be using the upper left-hand corner of the, the actor.
And we got to saw that briefly,
Exactly.
or got to see that briefly in the test application where we had that graphic that would go off screen and then reverse its direction.
Right.
So if this is indeed the case now, we need to change the velocity so that the current actor is moving in the up direction, and up is negative y. So we'll take self.velocity, and we'll set the y value equal to the result of negative math.floating absolute for the current velocity. Self.velocity.y. And that takes care of bouncing code there. Now, one other thing the ball needs to be able to do, and that is to detect when it has gone off the left and right edges of the screen. So, to do that, it's just a few more checks to put in place here. The next if statement will check to see if we've gone off the left side of the screen. So if self. Now, the way I want this to work is I don't want to count the balls off screen until it visually is completely off screen. That means if it just hit the left edge, the effect we would see is the ball would hit and then disappear and then reappear in the center of the screen. I want to wait until the right edge of the ball actor is completely off screen before we come back as true.
So that'll look right.
Exactly. Now, of course, I could do all this through offsets taking the width of the actor into account, but we are getting that screen rectangle, and that rectangle has an attribute called right to represent the right edge of the screen, so we can simply use that and we won't need any further offsets. So if we do self.getBounds.right, and if that value is less than 0, then the right edge of the rectangle has gone off screen. Now, what I'm going to do here is just drop a comment momentarily because the method that gets called here has not been defined yet. So I'm going to say call launch method. Just as a note, because as soon as we implement that method, we'll turn back around and put it in place here.
Okay.
But before we move on, I want to make sure that we also check the right edge of the screen to see if we've gone off in that direction. So we do an elif self.getBounds.left. Though I imagine, alright, I'm going to change this just very slightly. That is going to be exactly equal self to a self.position.x, because left edge of this imaginary rectangle is also going to be where our position in left is.
That's right.
And if we need proof of that, here we go. That rectangle is self.position.x. So we'll cut the chase and just put this in place here. So if self.position.x is greater than screen width, then we have gone off the right edge of the screen. And again, I'm simply going to jot this down as a comment to call the launch method. So that means now we need to address that launch method. So we'll define a function called launch, and that method is going to be looking at the current instance of ball, and it is also going to require a speed argument. And let me make sure I drop the colon on so we can drop into the launch method. Now the first thing that needs to happen inside of launch is the ball should always be launched from the center of the screen. So upon calling this, I'm going to make sure that this instance sets itself to the center of the screen. So we can call the center xy method. That will get us centered back up. Now I'm going to make a variable that I'm going to use to control some random variance. As a matter of fact, let me back up just a little bit. The idea here inside of launch is that we want to pick a direction. So imagine if you will, a point in the center of the screen and a circle that goes all the way around that. Mm-hmm. That circle could represent a rotational angle. If we point the ball, well, I won't say point, but if we direct the velocity in that direction around a circle, then we can simply pick any direction in 360 degrees that we would like the ball to begin traveling.
Okay.
Now, all the calculations we're going to do here are in radians, but we can get the same effect. The idea here is that I do want to put a further amount of control, though. I don't want to have a full 360 degrees as a possible spawn direction, because then we could launch directly up or down, which would result in the ball bouncing up and down infinitely with no ability for the players to reach it. Mm-hmm. So I want to limit the angle in which the ball can be launched from. And then to that limit, I also want to apply some random variance, so we don't get the same angle every time. And that's actually the first value that I'm going to get as part of this calculation is a variance value. So I'm going to make a variable called var, which is going to be equal to a random range. So I'm going to use random.uniform, and uniform will allow us to get back floating point values. And here we get to specify a range, what range we would like to get our numbers back in. So I'm going to give a range of -1 to +1. So this gives any possible value within a range from -1 to +1 or anything in between. Mm-hmm. Now, once I have this random variance, I'm going to use that in conjunction with pi to calculate an angle. So I'm going to make an angle variable. We'll set that equal to the value of math.pi divided by 2 plus the variance. And a quick explanation of what's going on here. Math.pi is, of course, going to give us 3.14, which is half of a circle. A full circle, full 360 degrees in radians is a value of 6.28 for whatever is 2 pi. Mm-hmm. In our case, what we're going to do is get half of a circle by pi. So already here we have half of a circle. Now look at what we're doing here, though, is we're taking that half a circle and further dividing it by 2. This gives us a quarter of the circle. And the reason I did this is because we're possibly adding to or subtracting from that value. If I left a full half circle, what could happen is we could be pointing straight up, and then plus the variance could actually cause the ball to go in the other direction. Mm. You'll also note that with this half circle up until now, the angle is only going to be facing to the right. If you go in and work out the angle to how that would affect the velocity, mm-hmm. we'll only have the ball launching in the direction to the right. If we want the ball to move to the left, we'll simply add 180 degrees, or in radians we'll add pi, and we'll do that based on random.
Okay.
But let's go ahead and get some of that in place now. So again, this coming up with a value that will give a range not quite the full values for pi, so not quite up or down. That's why we've got this first limit on it here. And then the variance will simply give a nice random effect. Now after we have determined this angle of some random direction to the right, I'm going to run a check. We're going to run another random number, and if that comes up as 0, so basically a 50-50 chance that the ball could go in the other direction, that is to go to the left. So we're going to run a check where we run random.randint, and we're going to get an integer in the range of 0 to 1. So this gives us our 50-50 chance because here the random number can only be 0 or 1. We'll do a check to see if that value is equal to 0, and if that's the case, then we'll say that we want to go in the left direction. So we'll take our angle and we'll add 180 degrees to that. So in radians, that is a value of pi, so we'll feed in math.pi. And let's see, now that we have an angle calculated, we need to turn that angle into a velocity. We need to turn it into a vector which points in the direction of that angle. And to accomplish that, we'll use sine and cosine. So here we're going to begin setting up the velocity vector for the ball. So self.velocity. And we'll first focus on x, which will be set to a value of math.sine of the given angle. And then I'll copy and paste that line, and we'll set the y component equal to math.cosine for the given angle. And that should return a unit vector back to us. That means the velocity should always have a length of 1 after this operation is run. Now we're given a speed argument here. So now we can use that unit vector. That's very convenient that it is a unit vector, because now multiplying against speed will give an overall magnitude for that vector that will represent the on-screen speed. So that means we can simply take self.speed and multiply that, or excuse me, self.velocity,
yeah,
and multiply that by speed.
For those wondering about Logan's spelling right now, it's actually doing quite well. What people don't realize is it's about 4:40 in the morning, and we've been going since, well, yesterday morning.
So when the brain tries to comprehend the left edge of the right side of the screen, spelling somehow seems to get forgotten in all of that.
Yeah. We just really wanted to get these videos in today, so yeah, we've just been pushing it. Okay.
And one other thing I want to do is take velocity times equals, meaning I want to say velocity equals velocity times speed, since we take unit vector and multiply that by speed.
Mm-hmm.
And once again, the fact that we can use our vector as a mathematical type is once again very convenient, as we have the scalar speed and we have the vector velocity.
That's right.
And the arithmetic is very easy here. So I think that takes care of the ball class. And now the next thing to do is to test it out and see if it's all working. So here under our game object section, let's look at our ball, and let's change it over to be an actual ball by using the ball class. Again, ball being an actor is going to require a texture. And now we're not going to worry about hard coding the velocity. Instead, we're simply going to tell the ball to launch and let it worry about where it should be going and how fast it should be going.
Now, of course, when we go to run this, we're going to have a... you're going to go the ball speed in?
Before I finish this off, I'm also going to have an error because I have managed to forget about the ball speed fed into launch. And if you remember, if we scroll very briefly up to the top of the game, we have a ball speed variable. So let's plug that in here to launch. So we'll launch add a value of ball speed.
And we still have another problem if we were going to
run directly.
Run this now.
If we try to run. So hit F5, make sure this gets saved. And there is, well, first we seem to have some syntax errors before we even get to running. The first syntax error here is that I have not indented where we were calling actor.move. As a matter of fact, I haven't indented any of this. Notice that not only actor, but the following things that I had intended to be placed inside of the move method are improperly indented.
Yeah, just that's what my note was right here to you.
Oh, I see. And Jason had jotted down a note, and I thought he was talking about the colon on the end. No, that's fine. But yeah, the indentation is in fact wrong here. We can quickly fix this if we select all the code we'd like to indent further, and if we hit Control right bracket, that will drop everything in.
Right.
So that's, again, if we look up here in format, we have Control right and left bracket that will allow us to increase and decrease indentation. So with that corrected, let's see if we have any other syntax errors. So let's run.
And we do.
We do. And that is down here. I've managed to forget to call our launch method. So I wasn't happy with a comment and there being no code. So inside of here, this is a simple call to self.launch. And we're going to launch by the given ball speed. And I can copy that line, paste it over the last one. Let's run it once again.
Another problem?
And another problem indeed. What we have going on here, if we look back, we see the window appear, so there are no further syntax errors. But back here in the Python shell, we do have some problems. We have an error where the name random is not defined. Random is an actual module you have to import into your script to gain access to everything that it can do. So what we're going to do is go up here to the very top and make sure that we import random. Now there's going to probably be another error. As soon as we try to run now, we get another error here that says math is not defined. Because remember, we're getting the math.floating absolute when we are calculating the balance off the top and bottom of the screen. And that means we need access to the math module.
And of course math.py as well.
Exactly.
So that should be good now.
So now if we run,
hey,
check that out. We've got the ball spawning, and as it goes off the edge of the screen it respawns, and if it hits the top of the screen it bounces. So let it run a few more iterations, maybe just see if we'll get lucky and have it hit the bottom of the screen. Because I do want to spend a moment and take note of how everything's working.
Beautiful.
So we are in fact getting useful random ranges, where if you imagine a kind of cone extending out from the center point of the screen, we have that as a valid range that we can use to move off the screen. We never end up in a scenario where we hit the top or bottom of the screen. Then we have that random check, that 50% probability of going the other direction. And so that works very nicely for producing an expected yet random result for the ball launching.
Exactly.
So with that, I think that wraps up everything I wanted to cover in this video. Again, the whole goal here was to get the ball class in place. So we've got it in place, we've got it tested, and it is all working.
And so with that, that will conclude this video. Thanks a lot.